Good afternoon, everybody. So my name is David Bott, and I'm the chair this afternoon for this, the first of the SCItalks that we're planning over the next few months to take advantage of the changes that pandemic gives you in communication skills. So just go through a few slides to make sure you know where you are, and then we'll get started with Tony Ryan's talk. So Tony will be talking about the second century of plastics, and I'll leave him to explain why that works. In case you see a picture of me later, this is a picture of me before the lockdown when I actually looked like something. Bryony and Tiffany, who will be helping with the question and answer session that will follow the talk, actually look that good all the time. So you know, you're in listen only mode. You cannot speak. It's muted by the software we use, and as I say, there'll be a question and answer session at the end of the presentation, but you can put your answers in or your questions in at any time through the question box on such. We'll be sorting them, prioritizing, and maybe even grouping them depending on how it works, and then do that. The hand up thing I think has been disabled for this, so don't worry about that. As I say, this is the first of a series of these SCItalks that's running over the next 3 or 4 months. In just under 3 weeks' time, Paul Hodges is talking about chemistry and chemistry in the UK. A few weeks after that, Robert Harrison is talking about how the digital revolution has affected manufacturing. And then 4 weeks after that, Melanie Loveridge is going to be talking about lithium-ion batteries and the way chemistry gets in the way of both making them work and eventually stopping them work if you don't know the chemistry. So I'll show you this list again later in case you forget it, but they're all really good lectures, they're all really good speakers. But today's lecture is by Professor Tony Ryan, now of the University of Sheffield. There are some words up there that I think cover his career. I've known Tony, we were working out just now for something like 30 years. And not only is he a great scientist, he has a passionate interest in the societal and environmental challenges of chemistry. And he also is a cracking good guy to spend time with, although I've long ago learned not to go drinking with him. But I mean, he is well known as a scientist and as a human being, and you know, his lecture this afternoon, I assure you, will be truly excellent. So without much ado, I'd like Matt to hand over to Tony and he will give you his talk.
Okay, well, good afternoon, everyone. I'm speaking to the title of The Second Century of Plastics. Some of you might wonder why the second century of plastics. Well, in 1920, the German chemist Hermann Staudinger convinced the organic chemists that polymers actually existed, that they weren't a variety of colloids. And he won the Nobel Prize in 1953. There's the beginnings of his paper. I assure you, I've never read it, down the bottom there. And his Nobel lecture uses many examples of natural polymers, cellulose and rubber, as well as the more obvious polystyrene plastic. And you can see a picture there of Hermann holding a polymer molecule in his hands that was taken for his Nobel Prize. So, from the first century to the second century of plastics, biopolymers pretty much got us started with the exception of Bakelite. And then after the Second World War, we really fell in love with plastics from fossils. Polyethylene, polypropylene, PVC, polystyrene, PET, nylon, my favorite molecules, polyurethanes. But now it seems that everybody hates them. I go to a dinner party, people say, what do you do? I'm a professor of plastics. The response is unbelievable. And I have to convince people that plastics aren't the problem, actually people are. So people always ask me about biopolymers and compostables, and I am of the view that they're not the answer for today, but they could be the answer for the future with biopolymers, bio-based polymers in particular. So could we make neofossils in the future? non-degradable plastics from agricultural waste, using photosynthesis to capture carbon from the atmosphere, use it for packaging, for other products, and then securely bury it and lock it up, taking carbon dioxide out of the atmosphere. So what we're going to do is we'll look at what's called the plastics problem, what people see as the plastics problem, then at the Anthropocene and CO2 levels, why it's important to sequester carbon from the atmosphere.
Yeah. We're having problems with people seeing your screen. Is it shared properly?
I thought so. How about now?
Yes, right. Okay, thank you.
Okay, so do we need to see?
Yeah, maybe go back to the pictures, yeah.
Need to see Herman again. So there's Herman with his polymer. We talked about how getting from the 1st century to the 2nd century of plastics, based on the publication on the 13th of March in 1920. So we are just into the 2nd century of plastic. And plastics have gone from being absolutely loved, the white heat of technology, the materials of the soup of the future, the man in the white suit, to being things that are hated. So we'll look at the plastics problem, we'll look at the Anthropocene and carbon dioxide levels, how we need to keep below 2 degrees global warming. We need to be negative in emissions by 2050. So we'll look at carbon storage and sequestration technologies. I'll explain how current bioplastics and compostables actually mean more emissions, not less. And then we'll talk something about agriculture, because understanding the link with agriculture and the carbon budget is really, really important. And once we've defossilized the energy system, then we can use renewable energy to turn photosynthesized carbohydrate into durable plastics and work out what to bury and when. So at the moment, 80% of the plastics used are basically in 4 classes: polyolefins, polystyrene, PVC, and polyesters are mainly PET. And then there are another 19% of other fossil-based plastics, and the 80% class are all fossil-based, made from oil or gas. And there's about 1% bio-derived plastics, and there's all sorts of specialities over here that we might never be able to deal with in the way I've described. But finding replacements in terms of properties is something that chemists are really, really good at. So I spent 8 years as a Pro-Vice Chancellor, and I came back to the research lab, looking forward to finishing my scientific career off and my academic career as a researcher. And just as I started back in the lab, Sir David Attenborough brought out the blue planet, and plastics became a figure of hate. I can't attribute this photo other than to the person who sent it me on WhatsApp. But this pretty much figures up, kind of describes my social life at the moment. Once you tell people that you're a professor of plastics, you're about as popular as a smoker inside. And the newspapers are in on the act, and it's really quite interesting how these stories are presented. So the Mail in 2017 ran this story. So it's about a beach in the Maldives, and the beach in the Maldives is on a lagoon, and this part of the beach faces the prevailing wind. So all of the trash from the island that's ended up in the sea gets washed up on this beach. And the story is about how garbage is ruining this surfing paradise. And you can see, there's all this garbage on the beach. It's nearly all polymeric. It's all made of plastic: chairs, bottles, buckets, spades, bits of packaging, a big bag that building aggregate came in, and obviously, to make a good photo, there's a surfer. And the surfer's looking disdainfully at all this rubbish. But the Daily Mail doesn't really mention the fact that she's carrying a plastic surfboard. It's got an expanded polyurethane foam core and a glass reinforced polyester resin gel coat. There's an abrasive bonded to the surface so she can continue to surf. She's wearing lycra pants and a quick drying nylon vest. And given the look of that hairdo, I imagine there's quite a bit of product in there too. And this brings out the dilemma: which bits of plastic do we want to get rid of, and which bits of plastic do we want to keep? But we are continually assailed by pollution caused by single-use plastic, and the people holding up this banner are holding up a banner made from, yes, you guessed it, single-use plastic. So it's really hard to not be judgmental about these things because there's a dichotomy in everyone's process: polluted by single-use plastic, wearing synthetic fibers. But now the situation we're in, we're absolutely saved by single-use plastic. Pretty much every piece of PPE that people wear, that the healthcare workers wear, is made out of some plastic or another. Despite the claims of some that you can actually make a plastic-free PPE, it's always polymeric and it's inevitably chemically processed. So in my mind, it's a plastic, even if it comes from some renewable resource. So the face shield, the face mask, the nitrile or latex gloves, the melt spun, hydrophobic, fluid repellent gown, the disposable apron, they're all really, really neat bits of polymer technology. And we have a real and present problem that's going to be made worse in COVID because people have gone more and more to single use. Because reuse and recycling are both difficult and expensive. It's often cheaper and certainly in many cases less energy intensive to make new packaging every time from virgin polymer rather than to make a package from recycled polymer that you've had to collect, clean up and wash, or even to have reusable packaging. Reusable packaging might save some of the energy, but it doesn't save much cost because it involves far more people. So single use shifts the cost away from both the producer, the retailer, and the consumer. And as a consequence, there's 8 billion tons of plastic in the Earth system. And if we continue at our current rate, there'll be 40 billion tons in the Earth system by 2050. And because of the way we are careless with plastic, 10 million tons a year gets into the ocean. There's about 3 billion tons on the Earth's surface and about 5 billion tons in landfills. And this great paper in 2017 in Science Advances basically surveyed the materials flow for all the plastic ever made, the 8.3 billion tons of plastic produced, the 2.5 billion tons currently in use, the nearly 5 billion tons that's been discarded, the 800 million tons that have been burned to recover the energy, and the recycled amounts. And what's really, really important is the pressure now on the polymer industry and polymer researchers is to increase this part of the diagram, the recycled part, and even better, a reused part through a circular economy. So when you talk to people about 8 billion tons of plastic, what does that mean? Well, you'd get 8 billion tons of plastic in an 8-kilometre cubed tube. So 2 kilometres each side. And actually, that's a big chunk of plastic, but it's not that much really compared to the size of the Earth. But if you turned it into cling film, which is 13.2 microns thick, and put it on a standard roll that you'd use in your kitchen, that's enough plastic to get you to Pluto and back 140 times. Or it's enough to cover the surface of the Earth, 510 million square kilometres, with 25% to spare. And that's the fundamental problem, that actually the plastic we have is finely divided in the main. And it's very well distributed. And when I was doing these calculations to work out what 8 billion tons looked like, I came to the realization that in 50 years, we've produced more plastic by mass than if we weighed all the people that have ever lived. That's 107 billion people in 150,000 years, at an average of 62 kilos each. 50 years to make more plastic than all the humans that have ever lived. And at the moment, we're producing enough plastic to equal the mass of all the humans that are alive today. And that's kind of frightening. Consequently, when plastics are reported, people talk about 1 million bottles a minute, the world's plastics binge as dangerous as climate change. Obviously, I took the mickey out of the Daily Mail earlier because it's not a paper I choose to read, but this was in The Guardian, of all things. 1 billion bottles a minute, the plastic binge as dangerous as climate change. Bullshit. This is a convenient truth. We can see it. But only 5% of oil and gas is turned into plastic. 8% is the petrochemicals industry, and a big chunk of that is fertilizer production. And 87% is burned to make carbon dioxide, causing global warming, and particulates, causing respiratory disease. And actually, there's been a COVID-19 bonus in terms of carbon dioxide emissions. And you can even see in air quality that the number of particulates has been reduced. And that comes with an economic downturn. It's a co-benefit of lockdown. But the plastic that's entering the ocean is the thing that's causing the most distress. And that's because we produce nearly 300 million tons of plastics waste a year. And because a quarter of the Earth's population live within 50 kilometers of a coastline, any mismanagement of that plastics waste, because it's either insecurely stored or it's just thrown on the ground as litter, it rolls downhill, it gets into watercourses, and eventually it ends in the sea. And it's definitely unsightly. It could be a real environmental problem. But I'm actually not so concerned about microplastics compared to, let's say, other particulates that come from diesel engines. But nevertheless, this move towards recycling plastic and making plastic circular so that we don't get the leaks, that we don't have a linear economy, is something that we at the University of Sheffield are working on. That's essentially what I'm not going to talk about today. So we want to be part of this new plastics economy, and the Ellen MacArthur Foundation has been absolutely fantastic in terms of raising the profile of the problem. And this drive towards circularity, recycling, and more importantly, reuse and being able to design and produce materials to be reused and efficiently recycled. And for a long time, I wasn't convinced about this renewably sourced virgin stock to decouple plastics from fossil feedstocks, because if we stop burning oil and gas, there'll be enough reserves for us to do petrochemicals forever. We just need to keep it in the ground and not put it in the atmosphere. But using it as plastic and using it responsibly and recycling it is something we can do over and over with durable plastics. And as we'll see shortly, making plastics from renewable resources can actually cause more carbon emissions than using petrochemicals. But people really want to do the right thing. And that's why cynical greenwash works. So here's a typical product. It's purified water. To me and you, that's tap water, something a man with a Yorkshire heritage won't buy. It's in a plastic bottle. The bottle's a plant bottle, and it's fully recyclable. It's fully recyclable because it's actually polyethylene terephthalate, PET, but it's called a plant bottle because the ethylene glycol, the E in the PET, is made from starch. It's fermented. So you're paying for tap water in a bottle that's actually only 30% plant and 70% petrochemicals. But what about plastics that are made from plants that are designed to degrade? Well, my friend and colleague Mark Madovnik at UCL has just run a big composting project, and it's proved something that we kind of knew anyway, that compostables don't really compost in a home composter, and you actually have to do something really, really harsh to them to make them disappear. And if they do disappear, what they disappear into in the compost is essentially water and carbon dioxide. So all the embedded carbon dioxide that was in them is then released. Consequently, it adds to the inconvenient truth that the convenient truth of plastics tends to hide. So when I was born in 1962, there were 320 parts per million carbon dioxide in the atmosphere. When my PhD students were born, and my eldest daughter was born in the late 90s, there was 360 parts per million. And today, there's 420 parts per million. And it's not that the curve's just rising, it's accelerating. Not only is the first derivative positive, so is the second. And there's no sign of it slowing down. And this carbon cycle that we have on the natural Earth has been disturbed by our use of coal, oil, and gas. So the plants and the soil are more or less in balance in terms of the cycling of carbon dioxide into the atmosphere and out of the atmosphere in year. And actually, you can see that cycling in the red line of the carbon dioxide levels, the summer-winter cycle of photosynthesis. And photosynthesis happens in the oceans too. So there's a net transfer in and out of carbon dioxide into the upper ocean, and there's some deposition in the deep ocean. But we're putting nearly 8 billion tons, that's a petagram of carbon per year, into the atmosphere. And on the stocks and fluxes diagram in the corner, the red lines are the anthropogenic, the human activities, and the black lines are the pre-industrial natural activities. And fossil fuels and all of our activities in terms of the economy are driving this change. So I was at the climate change talks in 2016. I went there by train, and it was clear that everyone was committed to keeping climate change below the 2-degree target and actually aiming for the 1.5-degree target, and made all sorts of commitments to do that. And all of them relied on rapid decarbonisation of the energy system, actually massive defossilization of the energy system, and in the future having negative emissions. But if you look at what's actually happening, our use of energy from coal, oil, and gas continues to grow. And all that the renewables are doing is adding more energy on the top. So we might shift in the UK from coal to gas and from coal to renewables. And actually, our carbon emissions in country are going down because we're importing more carbon dioxide in the form of finished goods. So decarbonising and defossilizing are absolutely crucial to our future. And there's lots of opportunities for chemists to get involved in this defossilization and decarbonisation activity, for catalyst chemists, for inorganic chemists, for physical chemists, for organic chemists making new molecules. And again, that's a whole other lecture. But decarbing electricity is kind of easy compared to decarbonising or defossilizing heat. So my good friend Grant Wilson, who's now in Birmingham, monitors the UK energy system. So this runs from 2015 to March 2019, and you can see the growth of the electricity from renewables, and that growth has continued. You can see the annual variation, and actually in the electrical demand, you can see the daily variations, and you can even see some spikes. So this spike here for electricity and this spike here in the gas with a weather event called the Beast from the East. And the blue line is the gas demand, because the blue line is basically, apart from the industrial baseline of about 100 gigawatt hours, is heat, domestic heat. And domestic heat it fluctuates with both the time of day and the time of year, and it goes in peaks and troughs. And it's this domestic heat, as well as process heat, that we absolutely have to defossilize. The defossilization of the current electrical grid will take care of itself, but it has to accommodate the transport fuel if we're going to move to electric cars and electric buses and electric trains. So what technologies are available to do that? Well, the Paris talks were full of all sorts of promises. So there was BECCS, which is bioenergy with carbon capture and storage, i.e. you burn plants, capture the carbon dioxide that's produced from the burning, and rather than release it to the atmosphere, bury it underground in some way. Or there's carbon capture and utilization. You capture the carbon dioxide and turn it into something else. There's direct air capture technologies where you take carbon dioxide out of the atmosphere. It costs energy to do that, and either bury it or turn it into something else. And then there are all the agriculture and forestry and other land use changes, so building new forests. Now we know that could give us about 4 gigatons of carbon dioxide a year, but actually we're currently losing forests, not building forests. And if we looked after our wetlands and allowed them to make peat, then that could take up about 4 gigatons of carbon dioxide a year as well. But actually, we're currently losing wetlands. And the same, well, with soil carbon sequestration, it's not so bad a story. In some places, we're adding carbon to the soil, but in many places, we're still losing carbon from the soil. And biochar is kind of, it's small, but it works. But for the fairy stories of carbon capture and sequestration, there are no demonstrable technologies at any sort of scale. But we do have in all of those land use and BECCS the hint of the ultimate carbon capture, and that's photosynthesis. So photosynthesis takes solar energy, splits water to release oxygen, and then fixes carbon dioxide into carbohydrate. And it's that fixing process that absorbs carbon from the atmosphere. And it absorbs a phenomenal amount. So the dry biomass production from photosynthesis on the planet is 250 gigatons per year. And agriculture produces 25 gigatons a year of dry mass. And of that, 5 gigatons is what we eat and what the animals we eat. And that includes 2.6 gigatons of cereals. And that leaves behind about 20 gigatons a year of biomass as agricultural waste. So how much of a plant's edible? Well, I'm currently growing hydroponic tomatoes in our conservatory because we had to shut an experiment down. And the edible part of a tomato plant might be a couple of percent. And most of that, as you well know, if you've had hydroponic tomatoes in the bad old days, is mainly water. If you're growing wheat, then what's called the harvest index, the grain to mass ratio, the grain mass to total plant ratio, in elite cereals is about 40%. But that still means that from a food perspective, we've wasted 60% of the carbon dioxide that was fixed because it all goes back into the atmosphere. And in a hectare of prairie wheat, you might get 8 tons of wheat and 10 tons of straw, and it's mainly carbohydrate. But what happens to it? Well, it's either left on the field to rot, which means it becomes CO2 emissions, or it's ploughed in as fertilizer, which means it becomes CO2 emissions in the main, or it's burnt in situ or collected for fuel, which means it becomes CO2 emissions. And traditional farming, turning over the soil by ploughing, typically lost about 30 tons of carbon per hectare because of the ploughing process. But modern methods of growing cereals in what's called no-till or zero-till agriculture uses a special drill to plant the seed and fertilizer. It needs chemical weed kill and genetic modified crops that are resistant to the herbicide to work, but it's very, very efficient in monoculture food production, not necessarily a good thing, and it's actually returning 2 tons of carbon per hectare per year into the fields. So now food production can become part of carbon sequestration as we restore the carbon content of the soil. And the technology that's needed is big tractors with wide wheels, lots of polymers and plastics in those, and then these fancy slot drill machines that have what's called a packer wheel that injects fertilizer below a seed so that when the seed germinates, there's a concentration gradient of fertilizer to allow the seeds to grow. And the plants are protected by an almost complete coverage of a crop residue. So for a US prairie hectare that produces 8 tons of wheat and 12 tons of straw, there's a carbon budget of 30 tons a hectare, there's 10 turned over in respiration, there's 20 carbon fixed, there's 8 in food and 12 in waste. And that waste is left on the field. 2 tons of it return to the soil pool, and 10 tons of it degrades and goes back as carbon dioxide into the atmospheric pool. And what I'm proposing to you is we use some of that. So when you do a global warming analysis from the wheat that you've grown in the field by doing a life cycle, what you find out is that actually the fertilizer is responsible for 40% of the global warming associated with a loaf of bread. The carbon emissions come from making the Haber-Bosch nitrogen to make the fertilizer. The baking, which you might expect with all that heat to bake the bread, is only 27%. And then the other cultivation costs, the running the tractor, account for 16%. So doing a life cycle analysis can kind of point you towards some interesting things. And in researching for this lecture, it turns out that the material flow and the CO2 emissions for fertilizer and plastic are pretty evenly matched. It's most likely a coincidence, but an interesting one all the same. And then what about this life cycle analysis? If you want to start a fight at a dinner party in Sheffield, bring out Badwa water and tell people, well, actually, I use Badwa water because when we do the life cycle analysis, it's better for the environment to drink sparkling water imported from France than it is to drink sparkling water that's only come the 25 miles from Buxton. So why is that? Well, when you do a life cycle analysis, you uncover spatial and temporal variabilities in products. And in the UK, the electricity used to blow the bottle actually dominates the CO2 emissions of the production of the product of a litre of water. And that electricity comes from burning fossil fuels. Whereas in France, the same amount of electricity is used, but now it's 80% nuclear. So there's far less CO2 emitted in the production of a bottle of French water than in the production of a bottle of Derbyshire water, even when you drink it on the Yorkshire-Derbyshire border. So what about bioplastics? The plant bottle. Read the label. 30% made from plants. That's the ethylene glycol. 100% recyclable bottle because it's still PET. So we've been doing life cycle analyses on various plastics, on fossil-based non-degradable plastics, on bio-based non-degradable plastics, on bio-based degradable plastics, and on fossil-based degradable plastics, and comparing the amount of carbon dioxide released on the production of the polymer. And you can see straight away that the fossil PET has lower emissions than the bio PET, that's full bio PET, that I'll show you in a moment. And the polyethylene and polystyrene are lower than bio PET, polylactic acid, which is made from fermented corn, and even lower than polyesters that are designed to be degradable and compostable, such as these butyl adipate terephthalate copolymers. So how do you make the decisions about what to use? So there's a great paper from the University of Minnesota Institute of the Environment, which does a comparative life cycle assessment of fossil and bio-based PET. So basically, to do the life cycle analysis, what you do is you have to draw a boundary around the process, and we're going cradle to gate, not cradle to grave. Each process has an energy input. And to make PET from fossils, you start with paraxylene, make terephthalic acid, start from ethylene, make ethylene oxide, then ethylene glycol, then they make PET, that's turned into bottle grade PET, and then blown into a bottle. If you want to use biomass for the terephthalic acid and the ethylene glycol, then you have to pre-treat, hydrolyze, ferment biomass to either make isobutanol or ethanol, and then convert that into the petrochemical precursor before you do the process of making the PET. So there's an energy burden on turning biomass into petrochemical feedstock because geology and time have converted biomass into petrochemical feedstock that we call fossil fuels and oil and gas. And those extra processes are currently at a high carbon intensity. So on a whole load of indicators, and I'm going to concentrate on the carbon dioxide emissions. So there's fossil-based terephthalic acid, wood-based terephthalic acid, agricultural waste-based terephthalic acid, and then there's fossil ethylene glycol, corn ethylene glycol made from food, switchgrass ethylene glycol made from a fast-growing grass that generates biomass, and wheat waste ethylene glycol. And on lots of indicators, and particularly on the carbon dioxide emissions, fossil beats any of the bio pairs. So should we burn more oil to make bioplastics? Obviously not. I've already told you, only 5% of world oil and gas goes into plastics. But does it make sense to make polymers from renewable resources? And the answer is, well, yes, it could. And it depends on the life cycle analysis. And we can only really afford to do it at scale when we've fully decarbonized the energy system, and in particular, when we've decarbonized the heat system. Because there'll always be enough fossil carbon for us to use as a chemical feedstock if we want to, but we absolutely have to stop burning it. And it turns out that our colleagues in the biorefinery world have taken all sorts of feedstocks, biomass that's from carbohydrates, from food grade carbohydrates, biomass that's from agricultural waste, lignocellulose, byproduct oils and fats and food grade oils and fats, and converted them into all the petrochemical feedstocks at C1, C2, C3, C4 that can then be built up into all of the petrochemicals we want to use and have got used to using and are an essential part of our everyday life. And more importantly, we can make all of the polymers that we can make from petrochemical feedstocks, from fossils, from this year's biomass, as long as we use renewable energy. So green polyethylene is on the way. So Braskem have built 2 plants, one in Brazil, one in the US, that basically take sugarcane that captures carbon dioxide, turns it into ethanol by first breaking it down with enzymes to make glucose, and then fermenting the glucose to make ethanol and carbon dioxide, which is released or could be captured. And then that ethanol's dehydrated, which requires a lot of process heat to make ethylene, and then polymerize, which releases process heat to make polyethylene. And then that polyethylene is indistinguishable to the polyethylene that you'd make from C1 and C2 coming out of an oil refinery through cracking or building up the molecular weight. There's also the academic community and the business community have worked together to make some fantastic new polymers. You can use seed oils to make polyurethanes. You can expand fatty acids from triglycerides with all sorts of functional groups and make polyurethanes, polyamides, polyesters that actually build the bridge between polyolefins and conventional step growth polymers. But biopolymer production's tiny compared to petrochemical polymer production, and I have to thank David Bucknell for this set of graphs. You can see the growth in world and European petrochemical production, and there's some growth, and there's quite a lot of predicted growth in bioplastics, but it's still not at scale. But interestingly, every bioplastic has a crossover with its fossil equivalent as the grid carbon intensity changes. because you get the benefit of what's called the avoided emissions, because you're not burning the agricultural waste, or you're not using that material in some other process and you're locking it up. So as the carbon grid intensity changes, as the carbon grid intensity falls in time, then the amount of carbon dioxide produced per polymer will start to fall, and the bioplastic part will fall quicker than the petrochemical part. So in this inset, there's the emission intensity of the grid, couple of predictions from the government, from BEIS. And the reason that you get these differences is that every polymer has a different balance in the source of the CO2 emissions. So whether it's the electrical energy used in the production, the heat energy used for the production, or the feedstock resource, the embedded energy in the feedstock resource that results in carbon emissions that are included in the calculation. And these calculations were made by Stuart Walker and Rachel Rothman in the Grantham Centre Plastics Research Group. So here's the blue line is the government's predicted fall in the carbon intensity of the electricity grid, and we've used that, and we've actually, okay, well, let's be a bit more ambitious, we've doubled it. So now you get bio-PET, bio-PLA, fossil polystyrene, fossil polyethylene, fossil PET, and the kilograms of carbon dioxide per kilogram of polymer fall with time because the energy intensity of the electricity grid's falling. And actually, you often get PLA replacing polystyrene in packaging applications, and come the mid-2030s, that will actually make sense as long as you don't allow the polylactic acid to degrade back to carbon dioxide. And this is cradle to gate, not cradle to death. So if you double the heat carbonization route, then some polymers change in terms of which is least impactful in carbon emissions. The crossover comes earlier, and the PET starts to really come down, the bio-PET. And this is based on a heat decarbonization. Now it's completely hypothetical, but you can see if we decarbonize heat as well as decarbonizing electricity, then things become a bit more interesting. Then we're actually getting crossovers in manageable timescales. So if you double the rate at which the electricity grid and the gas grid are decarbonized, PLA becomes much better than polystyrene in terms of its greenhouse gas emissions on manufacture. And bio-PET starts to creep down to the carbon intensity of fossil PET. And it might make sense to start making bio-PET at scale too. And I guess you're all thinking, well, where's the biopolyethylene on his graphs? And I'm sorry to say that we are doing those calculations at the moment, but they've turned out to be a bit tougher than we expected. So if we can make bioplastics at a lower carbon intensity than fossil plastics, it starts to make sense to think about burying them, because the carbon in a bioplastic is carbon that came out of the atmosphere essentially in the same year. So if we're going to make these neofossils, we're going to make new fossils by taking carbon dioxide out of the atmosphere and burying it, we need to lock that carbon up and safely put it down a hole. So it shouldn't degrade back to carbon dioxide and water, and that kind of rules PLA out. But PET might work if we can get it below the threshold and it can be locked up underground safely for a long time. And if we can do biopolyethylene at a lower carbon intensity than polyethylene from fossils, then we're well on the way to making neofossils, and we're doing that temporal life cycle analysis now, because we need to work out when to do it. And why is burying plastic better than burying carbon dioxide? Well, we know it works. Bioenergy with carbon capture and storage relies on burying carbon dioxide gas. And it's much easier to store plastic than it is to store carbon dioxide, because you're burying a solid. And the leakage potential is much, much, much lower. But we need to learn how to bury things competently, safely, and mindfully. So, if we could bury bioplastics, what would we be able to do? Well, if it's polyethylene, if it's polyolefins, then 300 million tons a year is a third of a gigaton. That compares with the amount of agricultural waste, which is 20 gigatons a year. So we've got a safety factor of 60. It doesn't take 60 tons, 60 times the amount of agricultural waste to make an amount of polymer. So we can use defossilized energy to, let's say, take 20% of the agricultural waste off the ground so it doesn't become carbon dioxide. We can still put the 2 tons of carbon per hectare back in the soil. And 0.3 of a gigaton of plastic actually contains 1 gigaton of carbon dioxide. So we could sequester a gigaton of carbon dioxide per year, every year, for as long as we wanted to use plastic. So, in this second century, what do we need to do? Well, we need to make sure we're not distracted by the convenient truth of plastics waste from ignoring carbon dioxide emissions. We need to concentrate on reducing the carbon intensity of our energy system. And yes, we need a circular economy for plastics. We need to stop it getting in the ocean. And we need to understand the benefits of plastics we want to maintain. But we have to balance them against the health and environmental costs. But most importantly, from my perspective, we need to work out when we can go back to a linear plastics economy, when we can start to sequester carbon dioxide by making neofossils. So, make fossils from plastic, not plastics from fossils. And hashtag put it back in the ground. Thank you very much.
Thanks very much, Tony. Excellent, provocative, and everything as usual. So the questions have been building up. For those of you who haven't asked a question, can I ask you 2 things? One, we have a very international audience this evening, so if you are asking a question from somewhere around the world, can you let us know where you're from, because that will just put him on edge a bit more. I understand some people have had a few video problems. We put out a message, apologies for that. We've never had it before, but we've got about 330 people watching, so we might have overloaded the internet. You've never done that before, Tone. Okay, so time for... Sorry, Siri just decided to answer me there. Bryony, do you have a question from the assembled questions to start Tony off on?
So first of all, thank you, Tony, for that very interesting and insightful talk. So we've got lots of questions coming through, and the first one is from Shayla Goyle, who says, Prof. Anthony, what are your views about the chemical recycling degradation technologies of PET? Do you think they are a viable pathway to controlling PET carbon footprint?
So yeah, so chemical recycling, from my perspective, especially for PET, where there's such a good mechanical recycling route, is the recycling of last resort. So yes, you can get them. You can get the monomers back by glycolysis. You can actually use chemical recycling to clean up some of the bad things in PET, like pigments and dyes, so that you can actually use it again for the same purpose, i.e. to make a bottle that you don't have to downcycle it. But I wouldn't see chemical recycling, particularly for PET, as being the primary way of recycling PET. In fact, the best way to use PET is to make the bottles 5 times thicker and to refill them, to wash them and refill them. And again, we've done the LCA on that, and depending on how far you transport them, it has a much lower carbon footprint.
Okay, Tiffany, have you picked one?
Hi, yep, so this is a question from Matthew Reeves. If it makes sense at some point in the future to make, example, bio-PET because of carbon impact, will the economics still prevent this?
Yeah, well, so economics, there's a reason that in my case that chemist and communist rhyme. So I don't think we can do what I've suggested based on economics alone. That all of these things need regulation and incentives, and business won't deliver this because it's expensive and it's difficult to make money out of. So yeah, business as usual means 500 million tons of plastic and yet more in the sea, because that's the tragedy of the commons that profit seeking brings.
Okay, Bryony, another one?
Yep, so Christopher Gortson says, amazing talk so far, thank you. Where do you see the optimistic decarbonisation of electricity and heat coming from? Are you simply advocating more nuclear, as this is an obvious but unlikely outcome?
No, I'm not. Well, so yes, I would be advocating more nuclear, because you need to do something to provide baseload. And nuclear is a fantastic way of providing baseload. Then you can see from the growth in wind. So, you know, we've not burned coal in the UK for quite a few days during this warm period, because the wind's been strong and there's been plenty of sunshine. So, you know, as renewables come down in cost per kilowatt hour when installed, and I'm sorry to say, I had to cut a whole load of stuff out about how we might go to decarbonise. But I think decarbonising electricity is relatively easy, right? Current electricity. Then it's how do you decarbonise? How do you increase the electricity to take over some of the heat? Because you really wouldn't want to be doing a lot of heat by electricity, certainly not at large scales. So then you need to think about, okay, so we can use the current petrochemical infrastructure, but we need to manage the process heat better so that we don't lose as much. But no, it's not a trivial problem, and we absolutely have to solve it. Next.
Tiffany.
Yep, so this question is from Rehan Pradhan. The same CO2 emitted after degrading PLA can be used to make new biomass and eventually new PLA. Does this not balance the CO2 emission?
So if you could collect all the PLA and compost it together, then yeah, you could keep reusing that carbon dioxide and not release it. I suggest to you that it's actually, if you make something that has biodegradable printed on it, then it kind of gives you permission to not look after it very well, because it's going to look after itself. So yeah, you can close the loop, and that's the kind of Ellen MacArthur idea, that you close the loop on carbon by making sure that when you do degrade the polymer, you capture the carbon dioxide and use it again. I just think practically it's very difficult because the materials.
Also, Tony, as I understand it, it leaves the same amount of carbon dioxide in the atmosphere, and your burying it idea takes it out of the atmosphere.
No,
as you
no,
say,
that,
like solid CCS.
So it's, I mean, it's exactly, it's plastic CCS.
Yeah.
So it stops the escape.
Okay. So, Bryony.
Yep, so next question's from Matthew Derry from Aston University. How do we persuade the public that burying these plastics is the way forward? Science communication from the governing bodies will be so important.
Yeah. So, and that's why the research we do isn't just chemistry and chemical engineering. So the plastics group in Sheffield and the people we work with has lots of social scientists, behaviour change researchers, policymakers involved, and it's going to be really difficult. So for the next 30 years, we need to say to people, circular, 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 circular. Don't throw a piece of plastic away. Recycle and reuse everything because it's destroying the environment. And then we're going to go, bonanza time, you can bury it now. And we're going to have to change our practices. But actually, the collection process of a circular economy can be the collection process of a disposal economy. So people will already have been socialized to, you don't throw plastic away thoughtlessly because it has value, right? And now the message is, the more plastic you use, the more you're taking carbon dioxide out of the atmosphere. And it can be socially responsible to consume more. Sounds like a bonanza to me.
Okay, next.
Yep, so we have a question from Timothy Reynolds in Belgium. So lots of people are talking about electrification of process industries, transport, especially road, is being electrified. So electricity demand will grow massively and all of it needs to be renewable, carbon free. How will we manage that by 2050?
Well, again, the market won't manage that, will it? So it absolutely needs investment. And I think because of the scale that's required, it needs planned and organised sovereign investment. So we would have to grow, in order to take up the capacity in the UK, for example, we'd have to increase our electrical power grid by a factor of 5 over 30 years. The last time that happened was at the start of electrification. So it is an enormous task, and it can only be done by policy, and it can only be done by large-scale investment, which means it can only be done by states.
Okay. Yeah, no, and they have to agree to do it and not argue with one another about where they bury it.
Well, no. Then there's all those the governance issues around this. So I'm really optimistic about the future because people want to do the right things and we can see the pathways. And the only thing that's stood in our way are vested interests and the governance structures.
Yeah. Okay. Next question, please.
So next question is from Joji Tanaka and says, hi, I'm watching from North Carolina, USA. I have a question regarding recent advancements in alternative depolymerizable polymers in some efforts for renewability via reusage of monomers, which does not release CO2. What are your opinions on this?
Again, I think so. Those things, and obviously, when you try and provide such a broad sweep as I have done this afternoon, you miss out lots of detail. Okay, so there's right at the beginning, there were those niche polymers. You're not going to be taking people's white fillings out to collect them, to bury them. Okay, there's various specialty applications It may well be that, you know, all the polymers that are used in microelectronic devices, yeah, you might want those to be made out of depolymerizable materials so you can collect them and use them again. So for small scale, high value products, then there will be a niche. And if we can do the chemistry such that there are not excessive carbon releases associated with that, then those technologies will thrive and prosper. But for scale, for the kinds of things that are 80% of plastics production, maybe actually no, most likely near 98% of plastics production, that kind of technology is not appropriate, in my view.
Okay, Tiffany.
So this is a question from Evan Lemieux. There are technologies that break down post-consumer plastics and convert them back to monomers. How do these technologies fit in your model?
Okay, so again, that's chemical recycling again, and it's in my view, it's the recycling of last resort because it's the most energy intensive, and there are many, you know, so Mike Shaver, Palamine in Manchester, is really keen on depolymerization to monomer. But what you can't do is you can't take the kind of material that's on the beach in front of you, stick that in some magic machine and get all the different monomers out. You know, thermodynamics just doesn't work that way. Yeah, I think that it's a niche area that'll apply to a small number of polymers, and it needs a lot of research.
Okay, Bryony again.
Hello, so question from Sina Spackman. What about the nutrients of the agricultural waste? While growing it takes up resources out of the earth, and if you take agricultural waste away instead of keeping it on the field, you risk dehydration, erosion, and nutrient loss. And fertilizer can't solve that because of runoff. What do you think about that issue?
Okay, so I thought I dealt with that in that the amount of agricultural waste is maybe 10 times more than we actually need to use to make plastic. So you're only taking 10% of it off the field. In the past, it's all gone. We absolutely need to do large-scale cereal production via no-till agriculture and enrich soil carbon. I wrote a research proposal about a year ago. There was one slide that just saw that coincidence between ammonia production and plastics, and those two things are intimately linked. And recycling nutrient is really important. That diagram didn't make it into the talk because it has a toilet associated with it. But it's something that we absolutely consider. Next.
Okay. Next. Yep.
So a question from Fiona Hatton from Loughborough University. With regards to burying plastics and putting it back in the ground, how would this be managed? If we do this now, generations in the future will deal with what we do now.
Yeah. So Fiona, back in 2002, I did the Royal Institution Christmas lectures. You were a bairn at the time, and I actually dealt with this question then. So because this is a long-term project, we have a chance to work out how to do the collection, right? So if you have the collection processes all set up for recycling that have material by provenance, when you bury it, you'll be able to bury polyethylene, you'll be able to bury polypropylene, you'll be able to bury PET. And actually what you're doing is you're creating feedstock for future chemistry, because you won't have to work as hard to get that back to something useful. And the important thing about managing the collection and the safe burial is to avoid things like this. So to avoid the waste. So actually having a circular economy in place in advance of a neo-fossil plastic economy allows you to develop all the infrastructure for safe collection.
Okay. Next question. You do realise, by the way, Tony, we have about 50 questions stacked up for you. How long do you have to see?
I'm gonna text downstairs for a cup of tea.
Yeah, that's the wonders of these modern webinars. Go, next question, please. I think it's Bryony's turn, isn't it?
Yeah.
Yep, there are so many, just filing through. What is, Valentin Bayer says, what is your view on pyrolysis to deal with plastic waste?
Again, it's another one of those, so, you know, in the hierarchy of things to do, then pyrolysis is kind of one step above burning in terms of recovering. So if you do pyrolysis to make oil, yeah, you do pyrolysis to make a fuel, what do you do with that fuel? Is that going to end up as a combustion, carbon dioxide and release? Then you may as well incinerate and collect the heat straight away. There will be situations where, you know, so PM perspex, polymethyl methacrylate, you can pyrolyze that and get the monomer back. If you've got a good circularity, then actually chemical recycling by pyrolysis might be the way to go for some specific polymers. Don't you think, David?
Yeah, no, I, as you know, I spent 4 years making sure that PMMA was the answer to every question. And yeah, 280 degrees C, it goes smoothly back to the monomer. Yeah. And you can use it for full value. It's the value of the recycler that counts, of course, because the higher the value, the cheaper the effective cost of cycles.
And that's why I keep talking about provenance. So I really do see this evolution of the way we deal plastic, with the way we deal with plastic through the circular economy means that we'll have better labeling, we'll have better collection processes, and therefore we'll be able to make the choices, the right choices for each material.
Okay, next question. Tiffany, this
time. This is a follow-up question from Matthew Reeves. He says, what intervention would you like to see from government to make the sustainable plastics vision a reality?
I guess the first thing I'd say is reuse. So we currently, it looks like we're heading towards a recycling circular economy, and not kind of going back to the future and doing a reuse circular economy. So I'd like to see a couple of things. So a reduced material set, because 50% of plastics is turned into packaging. So if you have a reduced material set, then it makes sorting easier. And then if you do reuse packaging over and over again, when it gets taken out of the stream, it's taken out in the factory, not separated by the consumer or the citizen. And therefore you have, after you've been used 20 or 30 times, you again have a material for recycling that's of known provenance. You know what's in it, so you can get more value for it. Mixed coloured PET is about a quarter of the price as clear PET. Again, just because you know what's in it, or more importantly, you know what's not in it. Done.
Okay, done. Next question, please. Bryony again. I am just looking at this list of questions, Tony, I have to say. You got the tea on the way.
Aristotle says, do you have any concerns associated with the leaching of plastic additives into the natural environment once buried?
Well, again, it's it's not the top of my list of concerns. to be perfectly honest. And again, I'm going to keep coming back to the same answer in a way, that we'll learn how to deal with the collection process through the circular economy. And then when it comes to putting things in holes in the ground, then we need to make the holes in the ground secure. And if the holes in the ground are secure, you know, you don't have water running through and leaching things out. That, you know, the dry, then leaching. If there's nothing to take out a leachate, then you don't have a problem.
Yeah, I mean, most people don't understand the science of how you put things into landfill and how you put them in clay things and that sort of stuff. So yeah.
Yeah.
Next, I guess it's Tiffany again, is it?
Yep. So Feb Hillman says, if chemical recycling is not the way forward, what would be the solution to PET trash? Mechanical recycling seems to have strict limitations in the quality of PET bottles that can be recycled. Downcycling will lead to accumulation for this downcycled material. Please, can you explain what solution would be primary if it is not chemical recycling?
No, so again, there's a hierarchy here. So if you can mechanically recycle and upgrade to reprocessing to the same bottle to bottle, for example, yeah, then you have to downcycle. If you can't downcycle, or there's not enough capacity to downcycle, then you can regenerate the monomers and repolymerize. But because that's so energy intensive compared to mechanical recycling, because you have to depolymerize and repolymerize, you wouldn't do that as the first step. So I'm not completely against chemical recycling. I just don't think that there's a magic chemical recycling machine that you can put mixed plastics in and get useful monomers out. And that we need to be really, really clear about what chemical recycling can do and when it can do it. I'm not ruling it out. It just wouldn't be my go-to recycling method.
Okay, thank you. Bryony?
So Edward Dean from Macclesfield says, what is the #1 thing an average person can do on a daily basis to assist the vision of decarbonising our electricity and heat systems?
So in terms of the heat system, so to reduce the carbon intensity, wear a jumper, turn the heating down. Think about how you travel. Do you go in a car? Do you go on a train? I have a PhD student who keeps on saying to me, you can be as vegan as long as you like, Tom, but if you're going to take those 3 flights a year, you've undone all of that. Consequently, I'm not a vegan.
I knew you'd get the stand up in at the end. And you've got Pitsy somewhere in the audience, so you've got competition. Next one, it's Tiffany back again.
So David Hall states that he's not clear what happens to your fossil plastics in the soil. Do they degrade to neo-fossil fuels, or do we reuse them in the future?
Well, no, so the whole point is I don't want to put plastic into soil. I want to put plastic into big holes, maybe even the big holes that we dug the original fossils out of. So it's going in a managed place, right? And if you remember right back to the beginning, then all the plastic ever made is 8 cubic kilometers. It's not actually that big a volume. So using big holes in the ground that we've already dug to get other things out of, so that we can line them and fill them full of sorted plastic so we know where it is in case we want to get it out again, seems to me to be actually quite a safe way of dealing with it.
Yep. Next, Bryony again.
So Patrick Cook says, we have a Bakelite coffin at our vintage plastics museum. being phenol formaldehyde, were they the first to bury plastics in the 1940s?
Very good. Yeah.
We like
yeah,
it.
yeah, nice one. I don't think
can't even begin to think how you're going to answer that, though.
No, I'm not. Yeah.
It's rhetorical.
Actually, if you have a cheap chipboard coffin, you're burying quite a bit of phenol formaldehyde.
That's true. Yeah. Okay, we're going to finish in about 9 minutes at 12:30 because Tony has a life and he still hasn't got his cup of tea that he ordered earlier. So Tiffany, back for another question.
Simon Gibbon, we need to consume carbon dioxide, so burying rather than reusing is better, isn't it?
Well, so yeah, and again, Simon, I think my perspective here is we don't have carbon sequestration technologies that work, and here in going from carbon dioxide to photosynthesized carbohydrate to non-degradable polymer back into the ground means that we actually take carbon dioxide out of the atmosphere and turn it into a solid that's not going to go anywhere. So it just, it seems to me that that's actually a far more viable technology than burying carbon dioxide that you've somehow captured from a smokestack.
Yeah, the practicalities of CCS have been defeating it for the last 10 years, but they're still trying. It's what engineers do. What can I say?
Oh, fair play to them.
Yeah. Next question. I think we're back to Bryony at this point, isn't it? I can't remember now. I've lost track.
So Sharon Todd says, how can we best incentivize the industry to move ahead as we need industry engaged? The stick approach does not work on its own.
So I think there's a couple of things here. So in what I've suggested, there's a really clear way forward for the petrochemicals industry. So when we're investing in capital in plant that's going to run for decades, we can invest in plant with an eye on what the future might look like. So building and clearly what you'd want to do is transport ethanol, right? So you'd collect biomass regionally, locally, do the conversion into ethanol and maybe even the separation of the ethanol, and then transport that to a cracker, because you'd want to do the catalytic dehydrolysis of the ethanol to ethylene in somewhere that was big, that had process heat to put into it. So for the chemicals industry and the plastics industry, getting on board is actually a path to sustainability for those businesses. We are going to have plenty of stick, though. There will need to be regulation, just like there's regulation coming now. And to go back to one of the previous questions, a deposit return scheme that would be deeply unpopular with drinks manufacturers and retailers because it brings costs to them, would go a long way to reducing lots of these littering problems, and the fact that recycling rates are so low. If you go to a festival, if not that you are going to do that this year, but you go to tram lines in Sheffield, there's not a pint glass to be seen because you collect pint glasses and you get money. So the stick can provide the incentives to make businesses respond to business growth opportunities.
Actually, you talk about the lack of litter in the present environment. I live in the countryside. I go for a walk. There's still almost as much litter around. Yeah. God knows where it comes from. Right. Let's make this the last question. So it's Tiffany, I think.
Okay. So Aristoteles Zographos asks whether you have any concerns associated with the leaching of plastic additives into the natural environment once buried.
We've dealt with that one. We've had that question before. Do you want to do another one?
Oh, yeah.
Refer to my previous answer.
There's somebody's been asking about nuclear, because you were very up on nuclear as not involving carbon dioxide, but of course it has other environmental potential problems. You want to riff on that for a while?
Yeah, okay. So again, more people have died from respiratory diseases caused by PM2.5 particles coming out of diesel engines and wood burners than have ever died from nuclear accidents. I think we need to properly understand risk, and if we properly understand risk, then nuclear ceases to be an issue that's anything other than emotive. Whatever we do, there's 7 billion people on the planet, right? 7% of all the people that have ever lived are alive today. Okay, we are going to leave a mess. What we have to work out is which is the least worst mess we leave behind.
So something for various world leaders to consider at the moment as a good way to finish the talk. Tony, thank you. As always, it has been enormously entertaining to listen to you. Thank you very much for joining. Please talk to us if you're interested in joining the SCI and learning more about the sort of things we do. Twitter, LinkedIn, Facebook, we're all over the place, but please keep in touch. We're here to try and, as it says in the bottom right-hand corner, be at the place where science meets business.